Okay, so today we are going to understand some more numericals on the power amplifier. So this is the first numerical, and it tells us that a single transistor is operating as an ideal class B amplifier with 1 kilo ohm load. Now you are having a single transistor, and that is the class B amplifier. So it means that the single-ended class B power amplifier will be used. When single-ended class B power amplifier, if you are talking, then there is only one transistor. This is not a push-pull amplifier, because in the push-pull amplifier you will be requiring two transistor, either in the complementary fashion or in the symmetrical fashion. So in this case, if I want to draw the transistor, then you can see that this Class B power amplifier, the operating point is located at the cutoff and or at the saturation. So in that case, you don't require any biasing circuit. Now you can see here, this is the resistance RC, or you can call it as the RL, that is the 1 kilo ohm it is given to you. Because normally you will have to put the collector resistance, or you can say the load resistance at the collector terminal. We are using the NPN transistor. So now this is connected to the biasing voltage, and to this, okay, so we will connect the emitter to the ground. Now this is the input signal which you want to amplify, but due to the class B single-ended amplifier, we will be able to amplify only the one half of it. Fine, as you can see that if I'm going to plot if I'm going to plot this IC and the VCE curve. So what is going to happen? The operating point will lie. Suppose we'll take that the operating point is lying at the cutoff. So in that case, this is the AC signal which you want to amplify. So now from this figure, you can say that the negative part has entered into the cutoff region, and as per the rule, only the signal which is in the active region can amplify. So in that case, you are not going to have the amplification of the negative signal. So you will get only one half of it. You can see here again, here you are going to get the one half of it. That's why we will have to connect the two transistors. So now a single transistor is operating in an ideal class B amplifier with 1 kilo ohm load, and a DC meter in the collector circuit reads 10 milliampere. So you can easily see that here the ammeter is connected, and this ammeter is going to measure the 10 milliampere. Fine. So DC meter means what? This meter is going to measure the average value of it. Fine. This meter is going to measure the average value, and the average value it is given as 10 milliampere. Now, how much is signal power is delivered to the load? So you can see that from this load line characteristic, you can find that the collector, just a minute, hold on, that the collector current is having only the half cycle of it. Collector current is only having the half cycle of it. You can see here you are not going to have the full cycle in the collector current. So if you take it aside, and you can see here, you are going to have only one half of it. Only one half will be amplified, other will not be amplified, that will be clipped off. So from pi to 2 pi there is no signal, and this is the collector current. So this is the peak value which you are going to get. Now, how to calculate the DC value? As you can see that this waveform is a DC only, because you are obtaining the waveform only in one direction. So this is the DC value, or you can say the average value. So how you are going to calculate? I think this is already discussed in the rectifier part. So now this is Im upon pi. Fine. Now, what is to be evaluated? You will have to evaluate the signal power which is delivered to the load. So, signal power means what? Which power you are talking about? Signal power means the AC power. Fine. So, AC power will be equals to how much? That is I RMS square into RL. So, why we have taken I RMS? Because we are dealing with the current only. So, you can also say that is PAC. PAC, it can be written as VRMS into IRMS, or it can be written as VRMS square upon RL, or it can be written as IRMS square into RL. Now, we don't have any information about the RMS value. It means that you will have to convert this into the peak value, because I think some relation has been there, that is Im by pi. So from here you can get the peak value. So here what it is to be written, Im upon root t root 2 whole square. So that one will be Im square by 2 into RL. So I think RL is known to you. You just have to calculate the value of Im. So you can see this is 10 milliampere. So this much is 10 milliampere will be equals to Im upon pi. So if you just solve this one will be Im will be equals to 10 milliampere into, just a minute, 10 milliampere into pi. So that one will be 31.4 milliampere is the value. So now if you put this value here in this equation, you will be able to obtain the signal power which has been delivered to the load. This is milliampere whole square upon 2 into RL. So I think you are going to get, just a minute, you are going to get the value. You can see here, simple. Simple, this value will be given. I think they have already, we have, I think initially before calculating the AC signal power, here it is, they have calculated IRMS. You can do it this fashion also. No need to worry about it. So this is about the first problem. Okay, so now coming down to the next problem. Coming down to the next problem. This is very important because the push-pull amplifier has been discussed. So you can see that with the load of 4 ohm, a push-pull amplifier takes a 3.2 ampere from the supply. So I think it will be better if you draw the wave, if you draw the circuit of it. Fine. A push-pull amplifier means what? The first transistor is the NPN transistor. Okay, so I'm going to draw the NPN transistor. This is the NPN transistor. Next is the PNP transistor. This is PNP transistor. This one is connected to the minus VCC, or you can say plus VCC. Then this is plus VCC. Then you can see the bases are common to both, because we will have to apply the AC input to this, and this is the load resistance. So load resistance is given as 4 ohm. So I think the NPN is going to amplify the positive half of the input signal, and PNP is going to amplify the negative half of the input signal. So basically this is IC1 and this one is IC2. So IC1 will be having only a positive half, because this transistor is going to operate, this transistor is going to operate only for a positive half. You can see here, for the positive half, this one will be forward. You can see base emitter will be forward biased, and the base emitter of this one will be reverse biased. So this will be cut off. When this is cut off, this will be acting as an open circuit, and this will be activated. So from here you can see the current is going to flow. So you are taking a current from the supply, so that is the IC1 current is going to flow. This is IC1. Now similarly, right, this one is IC2. Fine. So if I plot, just a minute, if I plot the, right, if I plot the waveform for IC1 and IC2. Okay, I'll plot the waveform. You can see here for IC1, this is the value. This is 0 to pi. Your first or you can say NPN transistor is going to work. And for IC2, I think this is already discussed in the theory classes. Pi to 2 pi, your IC2 is going to flow. This is, we can say, this value will be there. Fine. So, if you want to find the total current, or you can say the total DC current, fine. So this much, this is the DC collector current, we can say, and of the NPN transistor, and this is the DC collector current of transistor Q2. So if I want to find the total DC current, so total DC current will be found from this IDC will be equals to IC1 DC, then this is what IC2 DC. Now you can see here both these waveforms are rectified waveform. Fine, that is the half wave rectified waveform. And if you want to calculate the DC of it, so that one will be Im by pi, and this is Im by pi. Fine. So this is 2 Im by pi we have obtained. This is the IDC we can say. This is the IDC we can say. Fine. So now what has been asked, I think the AC power output has been asked. You can see here a push-pull amplifier takes 3.25 from the DC supply. This is the DC current. This is the DC current. So from here also you can easily calculate the things. That is 3.25 ampere is the DC supply. So you can easily calculate the value of Im, or we can write this Im will be equals to, because we want to calculate the AC power output. And AC power output will be what? VRMS into IRMS. Fine. VRMS into IRMS, and then that will be VRMS will be VM by root 2. Okay, so we'll try to write the things. Fine. So pi will go here and 2 will come in the denominator. This is the IDC. Fine. So now this is the first equation. I think you will have to write this as the equation number 1. Now the PAC will be equals to what? This is VRMS into IRMS. Fine. Now VRMS will be what? VM upon root 2. Fine. This is VM upon root 2, and this is Im, because you are going to get the complete cycle. No, you are going to get the complete cycle, so we can do that thing in Agar. So this is the thing, VRMS VM by root 2 into Im by root 2. So this one will be VM into Im upon 2, VM into Im upon 2. Now I think VM is VM, but if it is given or not. So instead of doing all the circles, what I can write this as VM will be equals to Im into RL into Im upon 2. Fine, VM will be equals to Im upon RL upon right. Just a minute, I think you will have to copy it down the things. Okay, so I'll write here. So now PAC will be equals to what? PAC will be equals to Im square into RL by 2. This is the thing, that is the AC power. Now Im, I think you have already evaluated 1 by 2 Im square pi by 2 into IDC ka whole square into RL. So the thing is that this is 1 by 2 pi square by 4 IDC square into RL. So putting down all the value, I think IDC is given to us, that is 3.25 ampere. So 1.1 by 2 pi square by 4 into 3.25 ka square into 4 ohm load. So this is the value. I think it is 52.124 watt. This much AC power is going to come. Fine. Now, in the next sub part, you see this part is why we have converted VM equal to Im into Rm, because in this part VCC is not given. VCC is given in the next part. So with VCC will be equal to 24 volt. What are the conversion efficiency and the dissipation? Now you can see that VCC is given. And you can from here also, this much portion is VCC only, fine. This much portion is, you can just see from this load characteristics. This one is the operating point, that is the cutoff. Cutoff is the operating point. So only one half is amplified for one transistor. This load characteristics which we have, output characteristic which we have drawn, is only for one transistor. Let us say it is for the NPN transistor. Fine. So in that case, this is the positive part, we can say, and okay, positive part, and similarly we are going to obtain the negative part in the VCE. That is okay. So now, what are the conversion efficiency? Rather conversion efficiency you will have to calculate. I think AC power has been evaluated, and so now you will have to calculate the DC power. DC power means what? PDC will be equals to VCC into IDC. So this is VCC means how much? That is 24, and this is 3.25. So if you just calculate the value, that is 78 watt. And okay, so dissipation means what? Dissipation means power loss, right? So power loss will be equals to what? Input power minus output power. Now what is the input power? Input power is PDC and output power is PAC. So 78 minus 52.124. That one will be your dissipation. So this is around how much? 25.87. Just a minute. 25.87 watt after doing the subtraction here. So now you can calculate the conversion efficiency. You can easily calculate the conversion efficiency. So conversion efficiency means what? Efficiency will be equals to conversion efficiency. You have to calculate. Just a minute. Some mouse problem is there. So efficiency will be equal to PAC upon PDC. PAC is how much? PAC is 52.124. You can see the conversion efficiency. This is very, I think, something which is appreciable. That is this is the thing that why we are using the push pull amplifier for our for the last stage of the operation amplifier. So I think this is around 66.82%. If you just calculate the value in percent, it will be into 100. That is the thing. So now the last part is what is the maximum possible dissipation. So I think you will have to write one note. So the maximum power dissipation occurs. Maximum power dissipation occurs when one certain relationship is to be satisfied. Is satisfied. For maximum power dissipation, you will have to follow this relationship. That is 2 by pi is VCC. So this is the condition for the maximum power dissipation. I think we have not taken this in the theory classes because it is not in your syllabus, but this question demands that concept. So the maximum power dissipation is going to occur only when VM will be equal to 2 by 5 VCC. If you want, I'll give the derivation of it. No need, because in that case you'll have to take the differentiation and all, and you will come to this condition eventually. So we will remove this, and we'll try to solve the things now. So now the okay. Uh, so now how to calculate the maximum power dissipation? So maximum power dissipation is again, because ultimately this is resistance only now. This is resistance only, and the dissipation is going to occur through a resistance only. And what is the resistance? Because ultimately the signal power will be available at the collector, and the collect sorry we can the signal power will be available at the resistive node, and the loss is going to happen at the resistance only. So in that case, P dissipation maximum will be equals to how much? Maximum. So for that, the formula is Vrms square upon RL. Fine. So this is Vrms Vm by root 2 ka whole square upon RL. So this is Vm square by 2 into RL. So now coming down to here. Now Okay. Uh, so Vm square, there is relation between the Vm and 2VCC. This is a condition which we have. Just a minute. Okay, so right. So P dissipation maximum will be equals to Vm. Okay, so 1 by 2 RL is there. This is 2 by pi VCC from this relation you have taken. Fine. So now you can easily calculate the things. This is 1 by 2 into RL, 4 into, sorry, just a minute. Something unwanted has been happened. So this is 1 by 2 into RL. This is 4 VCC square upon pi square. You put the values and you are going to get the answer here. Just the things are there. Okay, so if I just simplify the thing, that is 2 will cancel out. This is pi square into RL. Just put the value. 2 into VCC is how much? That is a 24 square upon pi square into RL is 4 ohm. So I think 29.18 watt is the answer. 20.9.18 watt is the answer. This is the second question which we have discussed. Okay, so I think the concept is clear to you. We will take one more problem, and so that will complete our push-pull amplifier part. Okay, so coming down to the next question. So I think this is okay. This is, if you want to refer, you can refer the PDF of it. I'll share the PDF with you. Okay. The ideal class B push-pull amplifier. Again, same question is there. The circuit diagram is given in the question, and so what has been asked? So you can see the maximum output signal power is asked here. So what is the maximum power signal output? PAC maximum. What is the thing? That is VRMS square upon RL. Fine. And this is VM square upon RL. Now, what is the value of VM? You can see here the some DC biasing voltages are given. So now coming down to the characteristics part of here, this is IC, and the operating point will be at the cutoff only. So you are going to amplify only one half of it. Now similarly, that reflection will be there in the VCE part. So now you can see that this much is the peak value. Fine. And if you just remember, this is VCC and this is VCC upon RC. I think the coordinates, the extreme points are there. So VCC upon RC and here. So you can see that the peak value is from this point to this point. Just a minute, I'll change the color. Okay, just a minute. I'll change the color and will come back to you. Okay, so now you can see here the voltage value will be this. So this is the peak value. You can see that this is the peak value now. So what you can write Vm will be equal to VCC. So in our case, it is given as 15 volt. So PAC maximum will be equals to 15 square upon 4. So that one will be, I think it is 2 now. So VRMS upon 2. Okay, obviously, because VRMS will be equals to what? VRMS will be equals to VM by root 2. I think this we have left it out. Okay, so that is the case. 2 into 4. So this is 28.125 watt. This is the answer. Now, the maximum DC power. Now, maximum DC power will be equals to what? PDC will be equals to VCC into IDC. So now you can see here IDC is the combination of the two current. Fine, because you can see here the two voltages are there. So when the two voltages are there, so because of this voltage, IC1 current will be flowing in this direction, and because of the second supply voltage, the Okay, because of the second supply voltage, the IC2 current is going to flow here. So in this case, this IC1 will be active only for the from 0 to pi, and this one will be active from pi to 2 pi. Fine. So in that case, the IDC will be equals to IC1 DC plus IC2 DC. I think in the previous problem we have solved this. So this is Im by pi plus Im by pi. Fine, Im by pi, and this is twice Im by pi. Twice Im by pi. Now, how to calculate this Im? So, what is the peak value? Vm will be equal to, you can see here. You can see Vm will be equal to VCC. Now, suppose if I want to calculate the right, so 2 by pi Vm upon RL, because you can write only a resistive load is there, so directly you can apply the Ohm's law there. So, Vm by RL. So, in this way, you can calculate IDC will be equals to 2 by pi. What is the value? VCC, it is 15 upon RL 4. So that one will be, I think this is the 4 value. This you can calculate, or you can keep it like this only. Okay, we'll put here. This IDC value will be put in this equation. VCC is known to you. VCC is known to you. So I'll put the values. What is VCC? 15 into 2 by pi into 15 upon 4. So this value is known to you now. So that one will be a 35.8 watt is the PDC value. Fine. So I think output power is there, input DC power is there. So normally in the push pull amplifier, you will have to follow you will have to calculate the DC current in this fashion only, because that time only, because two transistors are there and two transistor will be obtaining the two half wave rectified signal, so you will have to follow this method only. Okay, so now everything has been evaluated. So now you can easily calculate the conversion efficiency. So conversion efficiency will be what? Conversion efficiency will be efficiency PDC. PDC, just okay, just a minute. There's some problem with right. So that will be okay, P AC upon PDC. So PAC 28.125 and this is 35.8. So it is coming around 78.56% if you calculate the efficiency in the percentage. Now the maximum dissipation occur. The maximum dissipation is going to occur at which condition? When Vm will be equals to 2 by pi VCC. Okay, so this is the condition which we have just studied. Okay, so I think we'll have to remove all this thing. Okay, then 2 by VCC. Okay, we'll move forward. Okay, so you can see when Bm will be equal to 2 VCC upon pi, so P dissipation will be equals to what? P dissipation will be equals to the thing that is P dissipation maximum V RMS square upon RL. So this is Vm by root 2 upon root 2 ka whole square upon RL. So this one will be Vm square upon twice into RL. Vm will be equals to 1 upon 2 into what is the value? 2 by pi. 2 by pi VCC whole square upon RL. So I think after doing all the things jugglery, this thing pi square into RL, and you are going to calculate the value that is 11.398. So now here something, peculiar thing has been asked. What has been asked, you can see that we'll have to calculate the efficient maximum dissipation of each transistor. You have taken two transistor for the push pull amplifier, so in that case it will be divided by 2. So finally, and final answer is 5.699 watt. So in this way we have completed our numericals on the power amplifier. So thanks a lot for listening.